All right, ladies and gentlemen, hello and welcome back once again to the only coast to coast show all about the information economy. It's time for Inside Analysis. And folks, I'm so excited to have with me Dr. Moshik Cohen, a man I met earlier this year, but I feel like I've known him for many, many years. And he is quite the innovator. And to kick us off here, Dr. Cohen, I just want to say to you, congratulations on the success of Israel's air defense systems. I mean, I don't think you and I have spoken since that whole war broke out and the Iranians were firing thousands, and the Yemenis were firing thousands of ballistic missiles, including hypersonics, at Israel, and you shot down like 99.5% of them or something. It was just unbelievable. So you had to be proud, even though it was kind of a scary time. It worked, right?
Yes, yes, thank you, Eric. And again, great pleasure being here. And I miss talking to you.
Well, there you go. Yeah,
Yeah, so
yeah, I've studied
yes,
this quite extensively, and the fact that you have a radar system that can detect the difference between a bird and a drone at what, like 100 kilometers, the fact that you're able to identify and classify threats, understand what is a threat, what is not a threat, and then of course deploy relatively low cost drones and projectiles to intercept these things. It's really amazing. I mean, it's the Star Wars vision that Ronald Reagan had 40 odd years ago, but en masse and at scale. And even though here in the States, we talk about the Patriot missile systems and things of that nature, at scale, they cannot handle hypersonic missiles, and you folks did it. So, again, congratulations on saving tens of thousands of lives, if not hundreds of thousands, and really putting a stop to what was a terrible aggression on the world stage. So, anyway, tell us your thoughts about watching as all those missiles were shot down.
yeah, so actually I'm glad to see rocket science actually works. Okay, so
That's funny.
25 years ago, we were able to predict such edge case scenarios where many thousands and tens of thousands of missiles, drones, UAVs will attack our civilians population, not just military, mostly on condensed civilian populations.
Yeah.
So we designed and deployed a multi-layer air defense system. We have the Arrow missiles that handles the space, the ICBMs, the intercontinental ballistic missiles. We have the David Sling and Barak A that is the middle layer that handles the cruise missiles, the UAVs, and some of the drones. And we have the Iron Dome system that is the final shortest range system of Israel. This, again, within the Iran war, we were able to intercept the threats in more than 95% success rate. And using the discipline of the Israeli civilian, we were able to minimize the casualties.
Wow.
What it's worth to notice at this stage is the pace of innovation that the IDF and the Israeli population were able to demonstrate throughout this war. So giving you a few examples. The first example would be that I can share it now, that we actually had an arrow shortage during the war. So what we were able to do is to improve the Iron Dome system to cover for the arrow only with AI modifications. And our team took part of that. Okay, so we improved a missile defense system in war times and improved its capabilities by, I think, 5 times. And now it is capable to support much broader variants of threats, aerial threats. So this is a big wow for the IDF and of course for the DDR&D, which is the IDF's equivalent to DARPA, worked extensively 24/7 around the clock and deployed now combat-proven capabilities at scale. Second
That's
thing, which,
amazing. Oh yeah, go
yeah,
ahead. Go ahead.
it's actually amazing. Second thing that's worth mentioning is that in the beginning of the war, the IDF launched many hundreds of Iron Dome interceptors on birds, confusing them as drones. This is the actual resolution limitation of the radars and the detection systems that are currently deployed. And we were able to improve that with physical AI, okay, to differentiate between the movement of the center of mass and the wings of the birds, and from hundreds of kilometers, and by that differentiating them from the UAVs and the drones, and we nearly completely stopped this bird interception with the Iron Dome. And all of these amazing breakthroughs happened during wartime.
Wow. Well, it speaks to the fact that you have an architecture for this platform that allows you to do modifications in the software layer, in the AI layer, which then optimize what the physical assets do, right?
Yes, exactly. Everything is around the architecture. Yeah, and being a core and leadership, taking a leadership part in Israel multi-layer air defense, missile defense systems, we did our best to have the most scalable and future-proof architecture that is possible, that was possible in the time of development.
Hmm.
So this enabled us to software modify and software upgrade these systems during wartime.
Wow.
Yeah.
That's pretty impressive. And obviously here in the States, we have a much larger threat landscape as the attack landscape is humongous. And there are real threats. I saw you were posting on LinkedIn about Russia's latest announcement of nuclear powered missiles. Even and are they hypersonics too? Are they nuclear powered cruise missiles so they can travel low and they can go for days? I mean, and we've learned through hard experience now that Putin obviously doesn't really care about loss of life. I mean, 2 million people have died in eastern Ukraine as they are grinding forward with absolute reckless abandon. And now they're threatening to give these kinds of missiles to Venezuela. We need the Golden Dome here in the United States. And I'll do whatever I can to try to help you get into the mix because your system can be expanded to cover for the United States, right?
Yeah, exactly. Exactly. But I think not everything is so optimistic.
Hmm.
Looking at the United States, Israel, and the global threats map of our adversaries, the adversaries move fast. They move fast, and they target our weaknesses. Okay, and the biggest weakness of any air defense, every air defense system, is the detection system.
Hmm.
What you cannot see, you cannot defeat. And this is exactly what our adversaries know. And they are firing and targeting to our weakest spots. We are seeing it in the new development by the Russians and the Chinese, and how they distribute such extremely dangerous weapons to Iran and North Korea. So, so this is an extremely worrying trend that we need to be on top of. I think we already started seeing that in the last days of the wars between Israel and Iran, when a few missiles maneuvering hypersonics penetrated our missile defense system and created casualties and loss of lives. And this is extremely critical in these times when developing the United States missile defense, the Golden Dome.
Hmm. Yeah, we have to obviously be ever vigilant. And I know that a big part of the detection is having the machines to do all that. Obviously, the radar that you have in Israel is very, very powerful. But again, it's a much smaller landscape to protect. Here in the States, we have expansive territory, and we've seen a lot of strange things. I mean, in the last administration, we had that Chinese balloon hovering over our ICBM sites out in the West, and it went across the entire United States, and then they shot it down. And you're like, what are you guys doing? I mean, what I heard, what I read is that there is a very serious concern that they were gathering intelligence, that they were pulling information about the exact geolocation of these ICBM sites. I mean, this is real threat. that faces our nation now. And I think that in many ways we've been kind of lulled into a false sense of security about that. But what do you think?
Yeah, so first of all, as being a systems engineer, you need to look at the US as a tile area, okay? You need to select, let's say, a sample region for protection, prove the concept on it, and then scale the system,
Mm-hmm.
okay? And the foundations of such architecture should be based upon, should be founded on very strong detection layer. And then again, looking at the US system, I see it as a weak spot currently in air defense and in the Golden Dome. Then scalable software architecture, data processing architecture, and compute architecture. This is
Mm-hmm.
key because as we scale the system from a single area tile to the entire US, the data and the compute will explode. Okay, so the architecture must support intelligent tiling and scaling, hyperscaling actually, of the data quantities and the compute resources. Okay,
Mm-hmm.
but again, and again, this is key because there is now a hot discussion in the US right now, in the Pentagon, White House, specifically on the Golden Dome, whether choosing today's technologies and integrate them fast and deploy them into the battlefield, or taking a risk and going for more innovative breakthrough technologies. And this is a hot live discussion in the US um, top floors and leadership right now. Okay,
Mm-hmm.
and maybe 10 years ago or 15 years ago, if you were like in the early 2000s, maybe deploying as is systems would make sense. But today, in 2025, we are, as you know, in an exponential change times. Okay, things are changing very, very fast. So today's technologies are not future proof, will not defend us from the threats of today and tomorrow. And this is a fact. Okay. And now if you deploy expensive traditional technologies to a mega project like the Golden Dome, you're playing directly into the hands of our adversaries.
Mm.
They know your detection system will be limited. They know your interceptors will be expensive and limited, and they can easily financially exhaust your defense and your economy. And this is a huge trouble for us.
Mm. Yeah, that's a really good point. So we saw the U.S. Navy was fighting with the Yemenis in that region of the world for a couple years, and here in the U.S., I was, continuously disappointed in the media for ignoring this because they're very politically driven, and they typically want one side of the political divide to win at really any expense. And I think that's part of why we have this lack of genuine concern for what is taking place. Because your point is that even the most advanced systems from 20 years ago are incredibly vulnerable right now. I mean, we saw, just give you an example and get your take on this. I remember after Putin invaded Ukraine, that was in February of 2022. In May of 2022, some group, Dark Side, took down the Colonial Pipeline on the eastern seaboard of the United States, which is how I think gasoline was transported all up and down the eastern United States, and they shut that down. Now, at the time, the New York, the even the Wall Street Journal ran an article that said, "Oh, Dark Side says they have no connection to state governments." And I'm thinking, why on earth would you trust hackers who just took down our supply line? Like these people are lying, right? And it was the subhead of
Yeah.
the article. I'm like, this is clearly from Russia. They're clearly tampering with our systems as a threat to us, and they succeeded in taking. I mean,
Yeah.
you had no gasoline on the East Coast. That's an example. I mean, we never got to the bottom of it. I bet my last dollar that Russia was behind it or some Russian proxy to cause us trouble. But when you have that kind of a disconnect between the media and what's really happening in the world about very serious issues, that's very dangerous, right, Moshik?
Yeah, it's extremely dangerous, and these are one of the reasons for the U.S. leadership, especially the White House, being extremely worried on how to develop the best missile defense systems for the U.S. And this was recently encouraged by and supported by a new caucus that was initiated. Now it is chaired by Senator Sheehy, and the purpose of this caucus is to make sure that the Golden Dome does it right. It is being architectured right, it being developed right, and of course deployed right.
Hmm. Yeah, and you have to think, and maybe we can get into this in the next segment, but I'd like to kind of get it a bit into your architecture of the systems in Israel, because you mentioned there are a whole array of systems. You've got the Iron
Mhm.
Dome, you've got Barak 8, you've got Arrow, David Sling, but these all work together to identify threats, and then the appropriate system fires off what it needs to be able to handle those threats. And let's face it, I mean, we just saw proven in real time this system works. It works incredibly well. I mean, when you look at the number of missiles that were fired, and to your point, at civilian populations inside of Israel, not at just military bases, not at factories for building drones, things of this nature. No, they specifically targeted civilian locations. And you look at what's happening with the Russia-Ukraine war, Russia does the same thing. They are indiscriminate. They don't care. They're trying to blow up power stations and water stations and infrastructure basically to allow people to live their lives. I mean, that is the darkest of the dark, and it's happening in our real world. And I think that now we hear Putin talking about sending these new hypersonics to Venezuela, which, of course, is a narco state. I mean, the Trump administration has been blowing up these narco boats. Kind of hard to believe that they're just fishermen when they're loaded with tons and tons of fuel to make this long trip. And like, okay, I think they're bad guys. There's still some conversation about that. But in this next segment, let's kind of dive into what it takes to design a system like that from the ground up. Because to your point, there's hardware, there's software, there's AI that needs to be infused at various points in the architecture. And let's pick that up and talk about it in the next segment. We'll be right back, folks. You're listening to Inside Analysis. All right, folks, back here on Inside Analysis with Dr. Moshik Cohen. His company Apex, it's spelled AIPHEX, has put together much of the technology and architecture for the solution. And real quick, the folks behind you in that photograph, that's General Gutlein, right?
Yeah, is General Michael Gutlein, and he and the Office of the Golden Dome recognizes the breakthroughs in Israel and also our expertise. So we are trying to work together and collaborate to deliver the best Golden Dome for the US.
Yeah, that's amazing. And I do want to get into the weeds a bit about the architecture of this whole solution. So we mentioned you have the Iron Dome, you have Barak 8, you have David Sling, you have the Arrow system. Arrow takes the from outer space, right? Because some of these hypersonics, they literally go up into outer space and they point down and I mean I saw some footage of it and it's really terrifying. I mean, you see how fast they come down and the damage that they do. And the fact that you guys shot down what over 95% is just brilliant. But I mean, this is a long journey to get here. And I remember in one of your LinkedIn posts, you talked about an epiphany that you had late one night, a mathematical epiphany, because really you're a research scientist and a mathematician, and you're leveraging the power of math in systems design to be able to address these terrible threats, right? Talk to us about the foundation of that whole system. What is software defined, where you can put the AI into place, and how you can optimize in real time during wartime. I mean, you optimize the Iron Dome to handle even more threats. Talk to us about what goes into that whole process of designing and building that system.
Yeah, for sure. So as in a rigorous systems engineering process, everything starts with defining the operational scenarios. Okay, what it is that we want to protect from. Okay, and this is the key question: what is it we want to protect from? Where is the threat going to arrive? What are the quantities, the velocities range, the speeds, the altitudes, the warheads, and how we want to intercept them? What is the outcome that we want to get? You want to let them get into our border. You want to fire them out of, intercept them out of our borders. So this called CONOP. So the concept of operations and the threats definitions is the starting point of each air defense system design. Okay. Once we have that, we need to make sure that our detection system, which is the actual eyes of the air defense system, can detect, track, and classify the threats. Otherwise, they will create huge damage, right? Otherwise, it will be broken. So the detection system is a world, is a whole world. It's comprised of satellites, first and foremost, to achieve early detection, early intelligence, early warning. So, for example, Israel's satellites were able to, in the war, were able to recognize that the Iranians are preparing for a launch.
Wow.
Okay, so we actually knew that the Iranians were going to launch ballistic missiles, drones, and UAVs on us. This helped us focus our active defense, which is the radars, to the specific areas and improve the chances of active detection and tracking. So we have the satellite systems as the early and first detection. By the way, it can be combined with on-the-spot human and signal intelligence. Okay, because if we have some agents on the ground in Iran, they can inform us that there is some suspicious activity. Okay, so early detection, agents, human, and satellites is the first layer of every air defense system. But this is not enough because satellites cannot track missiles, especially not hypersonics, especially not cruise and low-flying missiles. So once the satellites and early detections detected a suspicious activity, the radars come into play, and they transmit a very high power radio frequency beam that interacts with the threat, with the target, and create reflections. The reflections are being processed by the radar processor, and then you create an image of the target, or a signal or a spectrum signature of the target. Based on this information, the targets are being classified. So a hypersonics, a drone, swarms, a cruise missiles, etc., etc. And then the information is being transferred into the semantic layer. So we have the early warning, the radars, the semantics. So this is the brain now, and the brain plans the optimal interception plan according to a predefined KPI, predefined set of KPIs. So it means maximum probability of success, interception, cost optimization, okay, multiple interception attempts, and more KPIs that are typically defined by the policymaker. Okay, once the interception plan has been selected, it is approved by the operator. Then it press the pickle, and interceptors are launched. Okay, so for the more expensive ICBMs, expensive and big and potentially non-conventional hypersonics, we use the Arrow missiles, Arrow interceptors, with clear target of intercepting them in space. We don't want them to reach to the atmosphere and penetrate. However, the space system is relatively slow. Okay, it cannot intercept fast cruise missiles, for example. Okay, so in order to intercept UAVs, large drones, and cruise missiles, we have the David Sling and Barak 8 systems, which are much faster and cheaper. Okay, so these are, so if we see, if we detect, if the semantics and sensors detect cruise missiles and drones, we typically also prepare the David Sling and Barak 8 systems, and only for short-range missiles and last trials, we actually use the Iron Dome, because this is the shortest range system, which suits more to Gaza threats. Okay, so very short range threats, and not to ICBMs and drones and cruise missiles. So, so the optimal interception plan and execution includes sensing, detection, classification, AI planning, and effectors optimization.
And you're actually able to classify what kind of weapon it is that's coming, right? This is a key part of the process. And what really impresses me, honestly, is of course the radar is very powerful going out, but then the reflections that come back, that's what you need to process. And it can be very challenging to process that kind of information. So you've got some pretty good algorithms that can determine based upon the feed, number one, what this thing is, but number two, its trajectory, because that's what you're really identifying for, right? You're solving for the exact trajectory of the weapon. Where is it going to be? Not at this moment in time, but at
Yeah,
a future moment in time. And that's where you send the ordnance to intercept it, right?
exactly. It's called smart proportional navigation with continuous PIP estimation. PIP is the predicted interception point. So we
Ah,
actually have a very smart AI-centric system that predicts the route, okay? And the interceptors are being launched to the PIP, okay, to the area of the PIP, and then they have very small error to close in order to get the interception.
wow.
Okay, it's quite nice. What an amazing feature that we have in the Israeli air defense system is the prediction where exactly the threat will hit or supposed to hit. And if it went ahead predicted to hit in a desert area, we will not launch any interceptor at all. We will save the cost and the energy. And this is combat proven for more than a decade now.
Wow. That's crazy. I mean,
Yeah,
it's
it's
really
really
impressive.
easy.
And some of the interceptors actually have the capacity to error correct themselves, right? So it gets launched, and then you have the capacity to communicate with that. And if if the perceived impact point changes, the device can actually change its trajectory too in real time to hit the target. Is that right?
Yeah, it's perfectly right.
Yeah. That's that's pretty impressive. And yeah, you think about so I have a good friend of mine here in Pittsburgh. I want to introduce you to him, quite frankly, because they're doing really amazing work with AI and with some of these new algorithms. But he was telling me their company is based in Israel, and one of his colleagues who's talking to him on the phone back when this is happening is, "Hey, I just want to show you what's going on here." And he held his phone up to the sky so you could see the interceptions taking place. He's like, "You guys are tough." I mean, they're just sitting there like it's like you made popcorn that night when the attack started, right?
Yeah,
But
we
this
made
is
popcorn at that time, and I think we owe our lives to these systems and to the great people, engineers, scientists, and of course operators that make everything happen.
yeah,
But then again, as optimist as we are and as proud as we are in these systems, um, they are not future proof.
right,
Okay, these systems, including the Israeli air defense system, is not future proof.
right.
Looking at the trend, we are now seeing the trends of what's happening in Ukraine. So we can see now swarms of thousands of drones and UAVs. Okay, part of them are just booby trapped, but part of them are really harmful, launched together. And the relatively low resolution of today radars thinks that there are one target or two target, and suddenly they see thousands. and you cannot do anything about it. So even if you can intercept 100 UAVs, you will still get 900 in your homes and schools and hospitals and universities. So it's quite scary. And looking in the upcoming 3 to 5 years, we can see coordinating swarms of hundreds of thousands, okay? And even more than that, UAVs and hypersonics, vertically launched, with changing routes. It is nearly impossible to predict their route. You need to actually measure and direct estimate the routes in real time, which is a completely different class of detection and tracking system.
Right.
So in order to future-proof our defenses, we need a completely new class of detection systems and interceptors. So the mission is only becoming more and more complex, but more and more exciting.
Well, you need a federated environment is really what it boils down to. And I think that what we probably want to have here is multi-purpose detection stations that all, when I say multi-purpose, they do other things basically, so they can help in other ways, but you need them all over the place. And that system has to have a communication network to know when one system senses something, when another system senses something. And these are the kinds of things that we need to be working on. And to your point, it's not just one technology, it's a whole array of technologies. You know, on the detection side, it's the classification, it's the compute necessary, it's the fact that you have new kinds of drones coming out. And I just looked it up. You talked about this before, that China manufactures millions of drones a year compared to less than 100,000 here in the United States. And you know what we've
Yes.
seen, God bless the Ukrainians, they are tough people. I mean, they are using.
Yeah, they're very tough people, but I think that a direct war with China will look completely different.
Yeah,
Completely different.
yeah.
And again, they're playing directly to our weaknesses, and we must be aware of that in order to protect the life of our citizens.
Mm-hmm.
This is not a game, you know. We 20 years ago, when we've been working on this system, we said, okay, no one will use them. Today, there is a near 100% that such system will be utilized.
Right. Right. And we see it. You know, I go back and I mean, not to get too far off topic here. And in the next segment, I'd like to talk about some of the other cool stuff that you're working on. But, you know, I'll say something relatively controversial. I look at COVID as an act of war. I think our current president, who was, of course, president before the last administration, I think he may have inadvertently started what I call World War IV with his tariffs and tough talk on China. And then guess what happened? All of a sudden this COVID virus gets out and spreads around the world in no time. And it's like, I've done the research. There are scientists who published papers talking about what they wanted to create, and it sure does align with what COVID looks like. So it's like, yeah, I think gain of function was in play, and I think COVID was an act of war. Think about it. When do you shut down borders between countries all around the world? And the answer is during wartime. That's when you shut down borders all around the world. So that's what happened. But anyway, folks, don't touch that. I'll be right back with Dr. Moshik Cohen of Apex. You're listening to Inside Analysis. All right, folks, back here on Inside Analysis with Dr. Moshik Cohen of Apex. That's AIPHEX. Look him up on LinkedIn. He's posted a lot of really interesting stuff out there. But we wanted to get into the full spectrum that is necessary to build this golden dome. And obviously, energy is a big part of that. Compute is a big part of that. Data is a big part of that. And we have to do these things economically. So, what are your thoughts on how to optimize the energy usage and really the next generation of data centers?
It's a great question, Eric, because when we developed the Israeli missile defense system, and let's call it the Iron Dome for simplicity, when we built the Iron Dome, our core use cases were we need to intercept hundreds of targets, maybe thousands of targets, and of course, not simultaneously. But so this imposed or implied a certain compute architecture. Okay, but now when you look at the Golden Dome and the threats when we just mentioned, we talk about coordinated swarms of hundreds of thousands, maybe million threats. It may be joined by hypersonics, ships, submarines, satellites, beam laser weapons, electromagnetic pulses. So suddenly the war becomes a huge data generator, okay? And to handle this data, to sense, to classify, to filter, detect, track that, optimize interception plane, iterate, do the battle damage assessment, all of that requires a completely different scale of compute. It actually already interacts with the current AI hyperscaler. And we are only in 2025, okay? And I didn't even talk about scaling the system throughout the entire US, okay? So now we are seeing that future air defense must have future compute. That they cannot rely on existing semiconductors, they must be future-proof. And now quantum computing and light-speed computing comes into play. So what we are building is a quantum computer that is full semiconductor, okay? So no strange, huge structures. Everything is implemented on semiconductor, from the semiconductor vacancy as the quantum emitter, throughout nanophotonics, logic devices, and direct electro-optical control in semiconductor, in standard CMOS, all works in room temperature and actually enable light speed quantum computing at scale at room temperature, okay?
Wow.
And once deployed, it should enable the power of a hyperscaler in the size of a shoebox. And this can be taken out of space and implement the vision of data centers on space, decentralized, safe, and hyperscaler computers. And what's as exciting as it can be is that this quantum computing is a completely different architecture. It needs new software and algorithms. Classical algorithms will not work on quantum computing.
Right.
So you need to rethink the way you solve problems to the quantum area,
Right.
quantum era.
Right.
This is amazing. You have the huge requirement for high performance compute. You have the new amazing architecture of the quantum computing with this unbelievable implementations, and now you have to rethink the systems engineering and the signal processing algorithms, architecture, and AI to be optimized for that compute platform, and you get a completely new generation, new class of compute, and
Yeah.
actually new class of problem solving.
Yeah, I want to throw an analogy at you and see what you think, because I keep trying to explain to people the difference between quantum computing and traditional or classical computing. And one of the examples I've come up with is that traditional computing, classic computing like we have today, is linear in nature, even though we can highly parallelize some jobs. And that's what you see with a lot of this AI companies like Databricks with their directed acyclic graph. They're doing parallelization of jobs to get them done faster. So you're trying to process a mountain of data, you parallelize the job. That's why you see all these GPUs everywhere. Because in gaming, and we can thank the gamers for all the GPU acceleration these days, because they're the ones playing games and creating a market for these GPUs. But with quantum, it's a much different story. It's really a multi-dimensional way of solving problems. And in that sense, it's more like the human brain, because the human brain can run many different processes at the same time. You could be thinking about your job while driving your car and eating something and like doing all kind of stuff simultaneously. It's difficult for computers to do that in a classic architecture. But with quantum now, it is a much more multidimensional system for being able to understand problems and thus solve problems. What do you think about that?
I have to agree with that, and double clicking on your hypothesis and your opening, the foundational structure of a quantum computer quite resembles the physical structure of a deep neural network.
Mm-hmm.
Okay, so the quantum computer is much more native and simpler for advanced AI implementation. Okay, so you can see this adaptive neurons, adaptive structure that changes weights and not have a specific linear value or digital value, when data can flow across this hybrid structure, and there are also dynamics, so you can change the shape, the model from transformer to encoder with dynamic channel attentions, all on a single compute architecture, which is amazing. So quantum computing is the next generation of, let's say, brain native computing and the next gen of AI computing.
Hmm.
And
Wow.
this is the reason why NVIDIA is already trying to get prepared to the post-DPU era, and they gamble on quantum.
Wow. See, this is very interesting too. And another way to describe it is that, there's an old expression in English, there's more than one way to skin a cat. And the point they make there is that there are lots of different ways you can solve things. And in the world of computing, that has really always been the case. There are countless different ways that you can solve for a particular challenge. You can build new models. That's really what we're doing now. We're kind of in the AI era, where instead of just relying on traditional database technology, where everything is the same as it was when you put it in and you pull it out, this is a much different dynamic with these neural networks. To your point, they can change weights and biases. They can morph. They can change how they process information, and that's how people process information. This is why you can learn new ways to do things. And the long point I'm trying to make here is that with quantum done elegantly, you can solve problems so much faster and so much more efficiently than you could the old-fashioned way. I mean, they're just really simple, even examples I can give. Like we had a show recently. I'm sure you're familiar with the ODBC and JDBC drivers, classic database drivers for pulling information. The company that does that is called Simba. They're actually a client of ours. It's part of Inside Software these days. Well, when people don't have these drivers, they wind up pulling Excel spreadsheets and then manually manipulating data and like doing all this stuff the manual hard way. Whereas if they had the driver, it would have been done automatically. Well, when I think about these very complex problems like the Golden Dome, like missile defense, like being able to identify and classify threats all across a country the size of the United States, you need a new solution to do that. You do not want an old-fashioned classic computing architecture where it's just like waiting for batch processing and overnight and all this crap. No, this has to be real time, and it has to be dynamic in nature because the threats change. And so I'm very encouraged that you're focused on quantum because, again, to your point, there are going to be a lot of jobs in quantum computing because we have to write new operating systems, we have to write new applications. They don't work very well. And I'll give you a quote, and they got about a minute and a half left in this segment. My one of my mentors in this industry, Dr. Michael Stonebreaker, he's the guy who invented the modern database about like 50 odd years ago, Ingress and Postgres. He's still around, by the way. He's on our list. He comes and checks out our webinars now and again. But he,
Impressive.
but he had this great quote, and this is 10 years ago on DM radio. He said to me something that cracked me up, and we'll pick this up after the commercial break. But he said, 80% of the code that has been written should just be thrown away. That's what he said. Because he's basically speaking to the fact that we have whole new architectures now, and this old code is just not going to cut the mustard. If nothing else, just think about the spinning disk. A lot of code was written to allocate to spinning disk as opposed to solid state drives. Well, solid state drives are a hell of a lot faster than spinning
Yeah.
disk. And now we have all this flash everywhere and like everything changes. So it's like you have to let go of the past in order to embrace the future. And I think that's what quantum computing is going to be all about. But folks, we got one last segment with Dr. Cohen coming up next. Send me an email if you want to be on the show, info@insideanalysis.com. That comes straight to me. We'll be right back. You're listening to Inside Analysis. All right, folks, back here on a fantastic inside analysis with Dr. Moshik Cohen of Apex. He's the guy who led the team that built the whole system that protected Israel against thousands of ballistic missiles from Iran and the Yemenis. God bless their hearts. I don't know what they were thinking doing all that, but I'll just throw it back over to you to kind of close us out. The Golden Dome, we need software, we need hardware, we need data centers, we need engineers, we need smart people like yourself working on this stuff. What's next? How can people help out? Like, what are you working on to get this done now?
Yeah, so to close the session, I want to mention the energy aspect of that. Because again, once you scale a system like a Golden Dome with interceptors, sensors, data centers, these guys will need huge amount of energy. And we already know that the grids are broken, are old, or fragile, or broken, and they cannot support the scale of the Golden Dome across the entire USA, and this is a fact. Okay, so and now you need to look for alternative energy solutions. If you look at the current renewables like the solar and turbines, etc., these are sparse and cannot meet the pace and the amount of energy that are required. Fossil is extremely problematic, and now we are into nuclear. Okay, nuclear energy is already decided as the only solution that can meet the scale and the growth of the energy requirements from hyperscalers to the Golden Dome. But nuclear is always 10 years and $10 billion ahead, right? You can see it
Right.
from Livermore to current leading companies. It's always 10 years and $10 billion away. So what we at Apex have been doing,
That's a good
we
one.
we took the fusion energy to the quantum regime. Okay, so we are able to engineer anatomically sized structures that reduce the Coulomb force. So instead of extreme plasma, hot temperature, etc., which creates plastic collision, which fuses the particles, we just convert this to quantum tunneling. So the fusion is much more native, much simpler, okay,
Wow.
and much more efficient and scalable. So this is what we also do at Apex, and we try to grow that into the 10 of kilowatts, megawatts, and gigawatt space in very, very small sizes to support the hugely growing demand for energy, as you must know.
Wow.
Okay,
So,
so in order to actually meet the challenges of the Golden Dome, and not just the Golden Dome, of future threats and future economy, society, and in the end, global sovereignty, you need to invest in the foundational technologies of AI, quantum computing, and energy.
hmm.
And this is what we do at Apex, because A is the AI and PH is the physics, and we fuse them together.
Wow. Well, I'll throw another interesting question at you. We're in this fascinating period of time now where, historically, developers have been the bottleneck for doing new things in the world of information technology. Now, because of AI, because of Anthropic and Claude and ChatGPT, all of a sudden, developers can move at almost at light speed. I mean, you can crank out code like there's no tomorrow. Now, you have to be careful about what you put into production. Obviously,
Mhm.
systems can be fragile and you can take them down. But this AI that we now have can be used to optimize all kinds of different enterprises, including nuclear power and fusion. And so are you guys using this, AI powered code capacity to move faster? Because now it's like the business side that is the bottleneck. It's the human side that has to decide what to do in the next iteration of some technology. And I'm guessing you guys are leveraging some of that too, right?
100%, yes. So, in essence, we are an AI-centric company, and AI is not just the product, is the infrastructure of how we build our products. So, as of 2015, already 10 years ago, we built small computerized AI engineers, did some things like reinforcement learning, genetic algorithms, evolutionary optimization, and neural network to design very complicated devices, okay, to model physical phenomena, okay, to extract material parameters at quantum dimensions. And in order to do that in the right precision level that will enable you to engineer quantum phenomena, not to guess and to find, but to actually invent,
Wow.
you need the capability of precision physical modeling, but also AI engineers. So at Apex, we have been building that to that philosophy for more than a decade now. So
Wow.
now we want to scale to the 1 megawatt and 1 gigawatt scales for the nuclear energy. We are literally building a small data centers to to actually contain our computerized engineers that will work on that. So
Wow.
we are still keeping small, very lean and muscular teams and hyperscale it with AI engineers.
Wow.
So AI is actually has been helping us to reach these breakthroughs when our limitation and the actual convention limitation just bounded.
Wow.
So use that, and this is not the end of the story, because when you get when you deploy a system, when you get to deploy a system, it's typically much more complicated and multidisciplinary than it was in the past.
Right.
And the system's parameters are changed across operational conditions, temperature, lifetime, aging, even fungus and moisture of the environment and components. And so you cannot assume that the system should be conditioned and operated the same. So we have AI sensors that directly interact with the physics, sense it in real time, and optimize the system with a nano brain as it operates. So we have this
Wow.
AI as an infrastructure and as an operator, and of course, and as an air defense brain, which does the mission planning and actual interception.
Wow. I mean, this is really fascinating because you're speaking to the fact that we're in a, hyper accelerated world right now when it comes to innovation. So you can use AI to improve the material science and the design point of the devices themselves that are going to leverage the AI. I mean, this is what we're kind of talking about here. So it's like when you have an engine that is focused on and trained on trying to optimize the physical structures themselves, that's when you can make, no pun intended, quantum leaps, right? In terms of innovation. Anyway, final closing thoughts from you.
Yeah, exactly. It's not just it's much more than the dimension. It's the material types, it's the geometry, it's the illumination condition. We go from this angle, from that angle. What is the substrate? What are the coupling between multiple elements? How do you dissipate the heat, or maybe even convert it back to electricity at the nanoscale?
Wow.
So this unbelievable combination of precision nanoscale modeling and AI is, I think, the foundation for the technology, human, and life of tomorrow.
Wow. Well, folks, look this gentleman up online on LinkedIn, Dr. Moshik Cohen. It's Moshik. That's a diminutive little Moses, is what that means. So you parted the skies as opposed to Moses who parted the sea, right? We needed to part the skies this time around. And Apex is a company, and we hope he's going to have success helping us with the Golden Dome. We'll talk to you next time you've been listening to Inside Analysis.